And when I say engine management, I'm referring to what's typically done by what's known as an ECU, or an engine management system, which is controlling things like the ignition and the fuel injection system within a car. That talk was a fairly lengthy overview of what these systems are and very roughly how they work and what some of the theory behind them was. This talk is a little bit more short and sweet. It'll be an update on the project that I was talking about then, because it's come an exceptionally long way in the last couple of years, as well as a little bit more nitty-gritty about how this stuff works and how the electronics and both the hardware and software side of the project works. All right, so a couple of years ago I set out to make an engine management system that was based on an Arduino, because why not? But that wasn't just a simple toy of a system, it was something that could actually be used in a decent way. I felt at the time that the various engine management systems that were out there were either exceedingly closed source and proprietary, or just weren't meeting the right niche. Now, the niche in my instance was to try and get something that was very usable and very functional at the price of around $100 USD. Currently the project sits around 130 to 150 USD. So it's not quite there yet, but it's a heck of a lot cheaper than the $1,000 that you can pay for a commercial system. So this is very basically what you get as an interface to an engine management system. This is simple gauges of what the system will report back. This is fairly typical for any engine management system, so I've tried to emulate it fairly closely to give a feel of what most people would be used to seeing. And I am making certain assumptions with this talk in order to squeeze into 20 minutes. But this is all around how we actually control an engine and what it's doing as far as fuel and ignition goes. So the system I have is called Speeduino. There's an example box of it there. It runs on an Arduino Mega 2560, which is quite a limited system, but it also has a lot of advantage in terms of being very, very simple to access, very, very, very easy to obtain, very, very easy to code for, and also sufficient for what actually needs to be done. A lot of people tend to look at it and go, well, that's, why wouldn't you use one of the ARM chips that's out there? But if it's sufficient for the job, I feel that it's not a bad way to go, and it certainly creates a very shallow learning curve compared to some of the other systems. This is a fair amount of automotive-specific talk here, but this is what the Speeduino system supports at the moment. There's a lot of stuff going on there, and I'll talk about that a little bit later in the talk about what the challenges are with making an Arduino system do many things at once. But most of that is now a fairly good base system for controlling engine management. As a very brief high level, I'll just talk quickly about the inputs and outputs that the system uses. So a typical output for an engine management system are fuel injectors. These basically operate like a very high-speed solenoid to be opened and closed to allow fuel in and out of the system. Fuel into the system. Some ignition coils on the right. These are fairly standard of what's known as a coil on plug or coil near plug ignition system, which is very, very common on modern cars. Down the bottom, some of your typical control type valves. You've got an idle valve here on the left. These come in 2 and 3 wire configurations. They are PWM controlled. In the center, there's a boost solenoid for controlling boost from a turbo, again PWM controlled for that. And the valve on the right is another style of idle valve, which is a stepper motor. And the Speeduino can control all of those fairly well. Typical sensor inputs that are used by the ECU. Top left is an inlet air temperature sensor to determine what the temperature of the air coming into the engine is. An O2 sensor in the middle up the top. These come in what's known as both narrow and wideband formats, and they indicate how much oxygen is remaining in the exhaust after combustion. Sensor on the right is a coolant temperature sensor. Now, similar to the inlet air temperature sensor, these are fairly basic analog 1 or 2 wire variable resistance type sensors. Fairly simple to read, fairly common as, both of those sensors will be found in millions of vehicles worldwide. Fairly easy to read. A manifold pressure sensor. So this is one of the ways we can measure load on the engine, is measuring the vacuum within the inlet. That's a fairly standard system from GM. You'd see that in many, for example, Commodores or anything around here in Australia. It's just simply returns a 0 to 5 volt signal, which is fairly easy to read once calibrated. And the sensor in the centre there is a throttle position sensor. These two down the bottom can be used for determining engine load or how much work the engine's being required to do. This is your base set of sensors that you need to control any engine, or control it properly. You can do without things like the O2 sensor or even potentially the coolant, the temperature sensors, but they certainly allow you to get much more fine-grained control of any engine. Now, the obvious one that's missing from here that I'll talk about in a little bit is an RPM and crank angle sensor, which is very, very critical for the whole process to work. So that's just a quick picture of a Speeduino system, mostly populated on that board, but not complete. That's the current version of the board. Now, it's for this version, it was very specifically designed to be a through-hole only board, so people could put it together themselves very simply. There's a surface mount design in the works at the moment, which will both lower cost and lower the space. The basic parts of the board that you get up the top left is all your injector driver circuits. Top right is mostly your power circuit. The purple add-on board there is a stepper motor driver. The 2 ICs are for ignition control. The 4 FETs there are for things like the idle control and boost control. And down the bottom are all your analog protection circuits. I'm going to talk about most of these in detail coming up. One thing that really surprised me working with this project now that it's started to take off is how many people are interested in doing electronics on cars, but don't exactly know where to start. Everybody seems to know and understand that putting electronics into cars isn't easy because they have very, very noisy power supplies. It's very easy to let the smoke out of whatever system you happen to be making. And one thing I found really interesting is that once I published the schematics for these boards, and they are very well tested, things like the power circuit, people started grabbing those and just using those as generic circuits in whatever automotive design they happen to be working on. So for example, that's the base power supply circuit that's used on the Speeduino. It's not overly complicated, but it is exceptionally well tested. That will survive practically anything that an automotive environment will throw at it. Nominally, a car system runs on 12 volts, and fluctuations anywhere up to about 20 volts are completely normal, and the occasional alternator dump of about 100 volts for a quarter of a second is pretty common too. So that will survive all of that without any problems. It'll also survive a reverse polarity, so somebody plugs the battery around the wrong way. Jump start conditions, if somebody plugs that in wrong and you get 24 volts and things like that. It's not an overly complex circuit, but it has been very well tested. That will work on virtually any electronics project you want to put on a car, and I promise you that it really won't die easily. When you want to get more complicated and you want to get proper results, you need to grow that a little bit to something like this. This down the bottom is the same circuit you just saw, duplicated up here again with a few more bits added on. All of that is to have a dedicated 5-volt rail for your analog sensors. So basically you have the same circuit duplicated with an additional precision voltage regulator on the output. All of this can be done on about a $2 IC that you can get now, which is what we're looking at for the new board. But for anyone who wants to maintain the through-hole design, and there are a lot of people out there who want us to make sure that there is still a through-hole board, we do have a design like that. As far as the input protection, that's the basic circuit that's used for all of the analog input. This is for the coolant sensor, which requires a 5-volt pull-up. So optionally, that 2.49K resistor gets dropped out for something that supplies a 5-volt signal. But again, that will protect against most of the noise that you'll get in an automotive environment, even if you're running the sensor wire through the engine bay. It certainly won't kill your ADC line. It'll clip out at 5 volts, so you'll be fairly safe. And the values there as far as capacitor filtering is reasonably good for most types of sensors. So again, those two circuits, the power one and the analog one, seem to have been used by a lot of people as generic circuits for whatever automotive projects they're working on, and I can highly recommend using either of them because they will work quite well for you. Which led to the next thing that I never expected with the project, of people just grabbing the schematics and putting together their own boards for it. This one's just one that obviously that someone's hacked up fairly quick and dirty in the background. The one on the right is one that somebody's adapted to, that will plug straight into an existing AC Delco ECU wiring loom. And that's used across many, many different GM or type Holden type vehicles, and that'll plug in and work straight away. The other thing I wanted to talk about as far as the inputs go, just before I get onto software, is how we do, a lot of people tend to ask about how you do crank angle sensing and knowing where the engine is. So I've thrown a couple of slides in here just quickly about this. We do what's called as trigger decoding on the crank, where we have a wheel that looks something like this. Now there's many different variations. I'll show another one on the next slide. This is what's known as a missing tooth sensor. So we have, in this case, a wheel that would have 36 teeth, except one missing, and it gives a pulse train, basically what you get below. From this you can determine both the RPM and the position of the engine. On a 36 type tooth, you get fixed accuracy to 10 degrees on the crank, and you can do a second and third derivative prediction between the teeth to find a more accurate figure. Speeduino allows for many different types of wheels. This is another one that you'll typically get on many 90s Japanese cars. Much lower resolution. You only get the 4 teeth, and you get 2 additional teeth, or 2 additional windows, because this is an optical sensor, of varying length and varying position. And you can see a basic layout of how that gets decoded up the top to figure out where the engine actually is. The other thing I wanted to talk about, there's lots of strange stuff going on with the software in this code, but one that might be of interest to people is what I've done around the PWM. A lot of the outputs that I talked about, the idle valve, the boost valve, all take a PWM signal from the ECU. Arduino is somewhat limited in that it fixes you to what pins you can use for PWM and what frequencies they can be running at. That's really annoying. For example, most idle valves will run between 120 and 160 hertz, whereas a boost valve will typically want about 30 hertz. A VVT valve might be anywhere up to about 500 hertz. And getting them all to run easily can be somewhat difficult on the Arduino. So what I did was sort of mess around with the timers that are available and came up with a system that you can use or that you can get PWM from for virtually any frequency on virtually any pin that you want. So at least any frequency up to about 62.5 kilohertz. What it does is use the existing PWM compare channels that are in the AVR chip and allow you to mix and match, I guess, on the same timer. So you can have 3 outputs, for example, on the same timer. So you can run idle, boost and VVT all at different frequencies and all with practically no overhead and whatever pin you want on the output, which is a lot more flexible than what you get with an Arduino as standard. Very, very little overhead, about 6 CPU operations per hertz from the PWM frequency. If anybody's interested in that, I'm happy to show you how that was done, because it's a nifty little thing that really increases the flexibility of the whole system. There's a very, very high level view of what the main loop of the Arduino is doing. To try and make it do different things at once, there's a lot of interrupts going on, but that's the basic sort of loop of what's going on. The fuel schedules, fuel and ignition schedules, all get called as an interrupt, but they're calculated during the main loop, and all the interrupt then does is turn an output on or off based on the timing. That means that none of the heavy load processing has to be done during an interrupt, and it makes it very because they're so time critical, it means that you're only doing very short amounts of things during the interrupts, and hence you get very accurate timing. Of the 8 high precision outputs, so 4 each for fuel and ignition, they all run to an accuracy of about 30 microseconds, which is not mind-blowingly accurate, but not bad for what the system needs. As far as accuracy on an ECU goes, 30 microseconds is good. The difference between about 5 milliseconds and 10 milliseconds is the difference between a car that will run and will not run, as far as a fuel pulse goes. And the difference between 5 milliseconds and 20 milliseconds is an engine going bang or not. So it is fairly time critical. That's most of the high level of what I wanted to cover. I've got a couple of videos if anybody wants to see things running. But does anyone have any questions? I did race along fairly quickly there, so yeah.
So I guess I'll go right to the mic. Good save. Sorry, where was this? So I guess after you get all of the hardware working, the most critical part is coming up with like sort of the tuning of the engine,
yes.
Right?
Yep.
So you've obviously done experimenting with your own car, or
yep.
I hope a car that can sort of doesn't mind if it blows up. But how do your settings compare to the stock settings? Is it like faster? Is it more fuel efficient?
It depends. So compared to a stock setup, you can get some benefit, typically without any other hardware changes. The big advantage of using an aftermarket ECU like this, though, is that it lets you change things that would not be possible with the standard ECU. So you can fit bigger fuel injectors. If you wanted to fit a turbocharger, you can. If you wanted to change the intake system or anything like that, you can't do that whilst retaining the standard ECU, not in its standard form, stock form anyway. So switching to something like this lets you do that, and that's where you get the real benefit from. That said, my experiment vehicle is a little MX-5, and it runs a lot better with this ECU than it ever did with the standard one. So that has a lot to do with it being an early 90s injection system, which is not that smart, whereas this is a lot more flexible than what that ever would have been.
I don't want to open a can of worms. It's going to take 4 hours. But where do you start with developing the ignition maps?
There's base map generators. So you can put in essentially max torque RPM, so the RPM that you get your maximum torque at, your engine capacity, your estimated maximum volumetric efficiency, and your RPM for max power, and you'll get a fairly good base map for both fuel and ignition.
And then you just fiddle with it?
Or you can auto-tune if you've got a wideband O2.
Yep.
Yep.
Do you do any CAN bus operations out of your controller?
Not yet. There is an add-on board for doing output of CAN for instrumentation, but not any input reading at this stage.
I think last 2 questions.
I was just wondering, the automotive industry is traditionally super secretive and pretty closed. Have you had any kind of feedback, formally or informally, from anybody in professional automotive industry about what they think about open source ECU control?
No, short answer. That there's been enough aftermarket ECUs closed source, yes, but aftermarket still, that have been doing this for a while now that I think they just tolerate it. A lot of the stuff that you need to do this that would have been secret has come out because of those types of systems. No, short answer, no, I haven't spoken to anyone from it, but I don't think it's a problem.
You mentioned you got a very accurate 5-volt reference. How are you coping with like the voltage drop across lines, long lines in the cars? Is it just calibration in software for getting the sensor values back accurately?
So you're talking about like the feed line and return line for a sensor?
Yeah, just long DC lines returning voltage back to the ECU
Yep.
through a noisy environment.
Yep.
Voltage drop, all sorts of noise, etc. How are you coping with that?
Yep. It's not too much of a problem. You address it in both hardware and software. So you try to filter as much as you can on the hardware side, but then in software you're really just watching for major fluctuations which would indicate noise and filtering them out. So.
No, I'm sorry we're out of time, but everyone